Okay, so this is now 1.4 out of Griffith's quantum mechanics, and we're going to be talking about normalization. Before we do that, if you wouldn't mind please liking this video and subscribing. I'm hoping to grow this channel as I start graduate school, so I'd really appreciate all the support I can get. And before we get into normalization, let's just talk about where we're at up until this point. So we have this thing called Schrodinger's equation, and the solution to Schrodinger's equation is psi. And we found with the statistical interpretation, I guess we didn't find it, but we talked about it, the statistical interpretation of what psi is that it represents, or at least the square of it, represents the probability of finding the particle between A and B when you integrate over that region. And then we learned a little bit about probability in the last video, and essentially what we saw is that the sum of all your probabilities have to equal 1. There's a 100% chance that essentially something is going to happen. Well, now we can apply that to our wave function. And kind of in an analogous sense, we can get the integral from negative infinity to positive infinity of our wave function squared dx equals 1. In other words, the probability of finding the particle, if you add up all the probabilities of where the particle could be, it's going to be 1. So if you went everywhere over all space, eventually the particle is going to be there, or at least somewhere. The particle somewhere is what this is essentially saying. Now, in general, if you have psi, when you solve the Schrodinger's equation, there's no guarantee that, it's not a very straight line, but there's no guarantee that this is true. But one thing about differential equations is if psi is a solution to a differential equation, any constant, call it A, times psi, is also a solution to the differential equation. If you took time derivatives or two spatial derivatives, you might get A double psi, A times d psi, dt, what have you. Go ahead and plug that into Schrodinger's equation, and the A doesn't change anything. The A will eventually just all divide out. I didn't mean to divide or erase that last part. So if psi is a solution to a differential equation, any constant times psi is also a solution. So we're going to use that to our advantage here. And this equation essentially becomes a squared, the integral from minus infinity to positive infinity of the square of our wave function equals 1. Or if you'd like, a squared is 1 over the integral from minus infinity to positive infinity of this term here. If you just divide it over, and you could even take the square root if you wanted. You could say, alright, well, A is this square root. But there appears to be somewhat of a problem. But before I get into that problem, you just might notice it now, that A might not actually be a constant. I'll get to that in a second. You might also be wondering about all the different solutions to the Schrodinger's equation where this isn't true, because there's plenty of them. But those are what we call non-normalizable solutions. Those wave functions are not normalizable. And those aren't really of any interest of us, so we're only worried about the normalized wave functions. That gets into something we'll talk about in chapter 3 called Hilbert space. But for now, all you need to know is that we're not concerning ourselves with those solutions. Okay, so that's number one. Number two is, you might say, well, our wave function, that's a function of space and time. So when you integrate that, there's going to be some correspondence with time. It'll depend somewhat on time. So A is not really a constant anymore. A would be a function of time. And that's a problem because, again, what I did here, well, I didn't do anything. I was just kind of telling you. If psi is a solution, then a constant times any solution is also a solution. Well, that only holds true if A is a constant. If A is now a function of time, this is not generally true. So now we have a problem because what we initially did to get here isn't working. But we can prove that A is not a function of time. And in fact, what we'll show is that your wave function, when we integrate the square of that, it's constant over time. Now, if you ever want to show if something's constant over time, what you really want to show is that the derivative of that something, so the time derivative of that something, is 0. If we prove that, then we know A is also a constant and everything is fine. So we're going to move this derivative inside the integral. Before, we could use just a regular derivative because once we integrate all of this, if we integrate with respect to x, well, you're no longer going to have x as a variable. But if we plug it inside, this full derivative turns into a partial derivative because we haven't integrated our function yet. So hopefully that makes sense for, I'm sure most people know that, but in case you didn't. Okay, so now we're here. Now if we wanted to take the time derivative of psi squared, remember, psi in general can be complex. So when we square that, we're multiplying psi times psi star. Okay. Well, this is just a product rule from basic calculus. So we keep our first function, take the derivative of the second, plus the derivative of our first function with respect to t times our first function. Okay. Now if we go up here to Schrodinger's equation, if we move this I and h bar around, what you'll see is that the derivative of psi with respect to t is equal to I times h bar divided by 2m. The second derivative of psi with respect to position minus I over h bar times the potential times psi. And if you wanted to find, so that takes care of d psi, if you wanted to take care of the complex conjugate, that's pretty easy. You only need to change the signs of any imaginary number and complex conjugate anything that could be complex. So this turns into minus I now over 2m times h bar. The second derivative of psi star with respect to position plus, because we have the sign change for I over h bar v times psi star. Okay. So we can plug all of this in to our equations here. So we have psi star times the time derivative of psi, which is right here. That's I h bar over 2m. the second derivative of psi with respect to position, minus I over h bar, the potential times psi, plus psi times the time derivative of psi star. So that's minus I h bar over 2m, the second derivative of psi star with respect to position, plus I over h bar v psi star. And then we can distribute and kind of group things together. So we have I h bar over 2m psi star times the second derivative of psi with respect to x. And then if we did that over here, you would get minus I h bar over 2m psi times the second derivative of psi star with respect to x. And then minus I over h bar v psi star times psi, and then plus I over h bar v psi star times psi. So obviously these terms go away, and we're left with just this. And we can of course factor out some of these constants here. So if we do that, we can factor out an I h bar over 2m, and we're left with psi star times the second derivative of psi with respect to x, minus psi times the second derivative of psi star with respect to x. And this is all equal to the partial derivative with respect to x of I h bar over 2m psi star d psi with respect to x minus the derivative of psi star with respect to x times psi. Okay, so obviously the constants, those could be factored out here if you wanted to. But notice what happens if you take these derivatives, these partial derivatives, you apply the product rule, you end up getting just this. So if you're unsure about this step, I think the best way for you to visualize it would be to actually just go ahead and take this derivative, take the derivative of this, keep this constant, this, keep that constant. What you'll find is you'll have your cross terms canceling. And of course you have to do your product rule here as well. So if you're confused about that step, I encourage you to work out the product rule, and then you'll see that they are in fact equal. Okay, so then the derivative with respect to time, we're going to take the derivative with respect to time of our integral from negative infinity to positive infinity, psi squared dx. What we just showed is all of that stuff. If we plug this inside our integral, so if we plug this inside our integral here, the derivative and integral are going to undo each other. So essentially you'll just have your constants, I h bar over 2m, that'll come out, and then this function, so psi star d psi dx minus d psi star dx psi will be evaluated on these bounds from negative infinity to positive infinity. And that's just from the fundamental theorem of calculus, if you're confused about that part. Now, the key to remember here is that psi is normalized. So psi goes to 0 at plus or minus infinity. So if you did the limit as x approaches plus or minus infinity of our wave function, Such an ugly wave function. I need to get better with my size. I can draw them nicer, but I'm getting a little lazy. That should be equal to 0. So essentially you're going to get 0 minus 0, which is obviously 0. So what we showed is that this whole thing is equal to 0, which is to say this whole thing is time independent. It doesn't change over time. That's what the derivative is telling us, which is exactly what we wanted to show that A is not a function of time. So it all worked out in the end. I thought that was really cool. It's not something I don't think you would intuitively expect, but once you use that trick, which is a common trick of taking its derivative and showing that it's 0, it ends up working out. Now if you go through the book, if you're working through the book, there's problem 1.4 and 1.5, and I'm pretty sure I've posted both solutions on my YouTube channel, so if you get stuck you can go there, but those would be 2 really good problems to do right now. In the next video we're going to talk about momentum and what that means in the quantum realm. So if you enjoyed this type of video, please give me a thumbs up and subscribe, and I'll keep posting. Thank you.